let us recollect the result. This blue colored text is the theorem. If f is bounded and probability that exit time is this exit time, correct, because the stopping time, the hitting time of the boundary, the exiting time to the, from the domain, if that exit time is finite with probability 1, okay, for all a in the domain, then any bounded solution of this Dirichlet problem df is written as E of x is equal to expectation of f of Brownian motion evaluated at the hitting time given w0 is equal to x. That means if you have Brownian motion at point x starting from there and then run the simulation of Brownian motion till the time Brownian motion hits the boundary, and when it hits, look at the location. At that location, find out the value of f, evaluate f at the location, okay, and you do that repeatedly, possibly a million times, okay, and take average of these numbers. That is expectation, correct? So that would give you another numerical approach to find out the solution u, okay. So that would give you u of x. Okay, so this is the proof which we have already seen in the last lecture. So here we have crucially used that u is bounded, okay. So here we did not put the condition that d should be bounded, okay. We did not put that condition. We just put one condition about the domain of d, of course, that is this condition, that it is such that exit time is finite with probability 1, okay. So this is one, of course, a property of the domain D, okay. So we just had this assumption, and then we say that, okay, not every solution but every bounded solution can be written this way. So this is just a recapitulation of the statement of the theorem what we have seen in the last lecture. Basically we used a dominated convergence theorem, okay, here, okay. For that we crucially required u is bounded. If u is not bounded, we could not have used this theorem and we could not have concluded this result, okay. So next we go to the point 6. In this we look at point A on the boundary of the domain. So this this del stands for the boundary, so del d, such that when you approach to the point on the boundary A from within the domain, that means x belongs to D and x approaches to A. So within the domain you approach to the boundary of the domain, and for each x you evaluate this function and find out the limit of this function. This is a function of x, correct, because this is conditional expectation of f of w tau d, that means Brownian motion at the hitting time. So evaluation of the function at the position where Brownian motion hits the boundary. So then that is a random variable, of course, because f of w tau d would be random variable, real valued random variable, and you take expectation of that random variable. But this is not standard expectation, this is conditional expectation, because we start Brownian motion from point x. For another point A, so because for various different x we are taking, for another point A on the boundary, we should of course consider another family of point x, okay. So that way x will be in the neighborhood of that point A, okay. So depending on A, we are going to get this neighborhood of A in the boundary, and there we are going to take this limit. So if this limit is equal to f of A, okay, so that need not be always true. If that is the case, okay, for all possible f bounded measurable, because we cannot say that, okay, this is the case for some specific f, but for all possible f where f is continuous at point A, then that criteria gives some property of A, correct, because this would be a property of A, okay. And not only that, it's the property of, what is the property here, which property it is highlighting? It is highlighting the positional property, that how that A is located in the boundary. So, basically it is saying that the property of the boundary or the regularity of the boundary at the point A. Let me go through this again, that what does it say? It says that this equality holds, okay, this equality holds for all f bounded measurable, okay, and continuous at A. If that holds for some particular point A in the boundary, then that is well behaved. That is well behaved in the sense that then the kind of results what we are looking at would go through. Okay. So, we are going to categorize, or we are going to select such points A, and we are going to call that A as regular. Okay. So, let us see that, okay, how do you do that. This is the proper definition. We define sigma d. This is the time, first time when Wt exits domain D. However, it is a little different, it is very close to that, but it is little different because here C greater than 0 is real. So, I have made it blue color to highlight this, okay, T greater than 0. Often what happens that if you start Brownian motion from the boundary itself, then at time 0 it might leave. Okay. I mean the infimum, whatever infimum you take, the infimum could be 0. Okay. So, time 0 it might leave. Okay. But we are excluding that case, the time 0 case. I mean even if we exclude, it does not mean that sigma d cannot be 0. Sigma d could be 0 because this at some positive time it is leaving, but it is leaving with certain probabilities, but that positive time could be as small as possible with certain positive probabilities, and infimum if you take, that could be 0 also, but we are not preventing that. That is allowed, but what is not allowed is that it is leaving the domain at time 0. That is not allowed. Okay. So, so here Wt not belongs to D, okay, when T is positive. Okay. So, and then take infimum of that, that is defined as sigma D. Okay. This sigma D is very close to the exit time, except that it is considered. So, sigma D is strictly not, I mean tau D is less than or equals to sigma D. Okay. Tau D, which we have already defined earlier, it is less than or equal to sigma D. So, a point A in the boundary is regular for D if probability that sigma D is equal to 0 given W0 is equal to A is equal to 1. Okay. What does it mean? It means that when point A is in the boundary, okay, point A is in the boundary. Okay. So, let me see if I have any picture. See, for example, A is here, okay, A is here, and D is this domain, okay, D is this domain. And now from here, if you start a Brownian motion running, immediately it can go outside, or it can stay for some time and can go outside. However, since this is that here locally the half of the part is inside D, half of the part is outside D, of course there is a positive probability that it will go outside. Okay. So, here sigma D, if you calculate, that it will become 0 here. Okay. So, it is a nice thing. Okay. So, here if that probability is 1, so the picture what I have shown, that has that, because sigma D, I mean, so every time with the probability 1, Brownian motion would go to the other part, correct, because there is a nature of Brownian motion that it would be restricted in only one half would be probability 0. Okay. Because whenever it touches a point, it oscillates there infinitely many often. Okay. So, sigma D is equal to 0, you would be able to get there. Why? Because the time when it exceeds the boundary there, the time would be as small, whatever small time you take, there is a positive probability that it would cross before that time also. So, if you take infimum, you would get 0 here. So, probability that sigma D is equal to 0 given W0 is equal to A, it would be 1, at those cases. Okay, so most of the cases, if you draw in a very nice way, it is like that. But of course, there are certain cases when this is violated, but we are going to see those examples in one or two slides next. If A is on the boundaries, such that this is strictly less than 1, then you call that it is irregular, that it leaves boundary, this sigma d is 0, that probability is less than 1. However, there is a 0-1 law. This is called Blumenthal 0-1 law. This says that if this probability is less than 1, this should be exactly equal to 0. Okay, this probability cannot be anything but 0 and 1. So if it is less than 1, it should be 0. So what is this law? Let us read it in the footnote, that f is in f0. f0 is the sigma algebra at time 0. Then probability f, occurrence of f given w0 is equal to x is either 0 or 1. Here what happens, that sigma d is that taking time t, but taking infimum over all possible these things. Okay, so the future time, if 0 is present, t is future time, and then smaller and smaller time you are coming close to 0. So that is you are approaching from the right hand side. Okay, so this sigma d is actually, this event is actually f0 plus measurable, f0 plus measurable. Okay, however, since the filtration is right continuous, so f0 plus is exactly f0. And therefore, if we apply now this theorem, because f is in f0, this theorem, we are going to get that, okay, this probability of this should be either 0 or 1. Here this, in more precisely, we can say that, okay, if we ask this question, this f, the event is of this particular form, the w0 belongs to a set gamma, belongs to some set gamma, gamma is some kind of Borel set, given w0 is equal to x. We know how does the probability looks like. It will be just indicator function of gamma. If x is in gamma, then it's 1. If x is not in gamma, then it's 0. Okay. So we understand that the rationale behind this Blumenthal 0-1 law, and then understand that, okay, this probability that sigma d is equal to 0, this conditional probability will be either 0 or 1. If it is 1, then you call that point A as a regular point for d. Okay. And if it is 0, we call this irregular point. Why the name regular irregular comes, that I am going to state later, but already the picture what I have shown there, it gives some indication that there the point A was on the boundary, where locally it looks like this is just half plane. Okay, half side here, half side there. Okay, so that means the boundary has no kink, has no very sharp edge. Okay, and for those cases, this is very intuitive, and this is true. On the other hand, this regularity would be violated for a very extreme situation. Okay, so you would see those examples. Actually, you would construct some particular example where we are going to compute these probabilities, and you show that, okay, a particular point is irregular. So consider d is equal to this annulus. Okay, norm of x is between 0 and 1. So it is a punctured open ball. Okay, and d is greater or equal to 2. Then the origin is in the boundary del d. Okay, and that is an irregular point, because if you run boundary motion there, you would always move out. Okay, with this thing. Okay, then the origin is in del d, and that is no, you'd always be inside the domain. You'd always be inside the domain, because the origin is in the del d, but origin is actually in the d complement. Okay, d complement, but it is in the boundary of d. But if you start there, immediately it would go to the inside the domain. Immediately to go inside the domain, and from 0, if you will see that, okay, how long it would take to come to 0, that probability becomes 1 if d is equal to 1, because if it touches 0, it touches 0, crosses 0 infinite many often. But when the dimension d is 2 or more, then if goes away from 0, okay, so it again returns to 0 with probability 0. It does not return to 0, okay, certainly. So it can only go beyond the boundary only through the outer region, and outer region is far away, 1 unit away. So if you find out this probability, sigma d would become 0, very unlikely. So this probability would become 0, okay, so it would be irregular. However, one can object here that, okay, for this particular example, the boundary is disconnected, okay, so it is manufactured in a particular manner that when it leaves then there is no other part of the boundary, and another part of the boundary is far away. So one can think that, okay, can one construct a particular example where boundary is connected and A is on the boundary, still one can get irregular points? Yes, that is also true. It's not very difficult. So if we consider, so this is the thing, for d is greater or equal to 3, there are connected open domain D with connected boundary with which contain irregular points. So this is called Lebesgue-Thorne. So this Lebesgue-Thorne, so for construction we first consider cylinder, so bounded cylinder. The height is 2. Imagine that origin is here, and x1 is between -1 to 1. So this is a 1, this is -1, and 0 is here, x1 between this, and x2 and x3, the other variables, where x2 square plus x3 square is less than 1. So it's like open disk here, okay, open disk here, and here x1 varies here. So you are going to get one open bounded cylinder, okay, solid open bounded cylinder. Okay, so now we call that as capital E, and what we do is that we take various different copies but different size of such cylinders, okay, and we call that Fn, okay, and instead of open cylinder we are going to take, say for example, closed cylinder, where x1 is 1 over 2n to 1 over 2 to the power n minus 1. So this distance instead of 2, it is like this difference between these two, okay, and this is actually basically half of this. So this difference is actually 1 over 2 to the power of n, correct, 1 over 2 to the n plus 1 over 2 to the n would be 1 over 2 to the n minus 1. So this length would be 1 over 2 to the power n, and then x2 square plus x3 square is less than or equals to epsilon n. So this radius is epsilon n. Epsilon n is now kept as free. We are going to choose latter, and then we take this union of Fn, okay, n is equal to 1 to infinity. So imagine that these Fn are like consecutive cylinders, because if n plus 1 would the right hand side of this would be 1 over 2 to the n, and left hand side will be 1 over 2 to the n plus 1, okay. So there would be decreasing width and decreasing length cylinders, okay, from right to left, okay, and would approach to 0. That means that towards 0, these cylinders, 0 would be a limit point of these cylinders, correct. 0 would be in the closure of this, but we take union of all this Fn, okay. All the Fn's are closed sets. Union of Fn is not closed, because 0 is a limit point of union of Fn, but 0 is excluded there, and we take E subtract of this, okay. So E subtract of this, so we subtract this this whole thing from E, because everything Fn, everything is inside E, correct, and we subtract everything, and for sufficiently small epsilon, everything is inside, and we take this set E1, but E1 is not assured to be an open set. We take interior of E1, E1 interior, this circle stands for interior, so that we call as D. So D is my domain. Okay, so does 0 0 0 origin in the domain D? No, because this is in the boundary. What happens that of course 0 0 0 is in E and not in this, so it is in E1. But when we take interior of E1, then 0 0 is excluded. Okay, this is excluded because it is on the boundary. Doesn't matter. So this 0 0 0 we just take, okay, is on the boundary, and then we show that this is an irregular point for certain choice of epsilon n. If epsilon n are chosen very wisely, then we can actually get 0 0 0 as irregular point. Unless you choose epsilon n in a decreasing manner and very wisely, you would not get it, because if you take epsilon n is equal to 1, say, all the time, you know what I mean, nothing. This is like, it's just straight cylinder basically. Okay, you are not going to get anything, but epsilon should be decreasing in a particular pattern. So let us see. So we construct Kn where this vector x is such that, okay, x1 is between this, x2 and x3 is equal to 0. This is nothing but the axis of the cylinders. So these are exactly the end points of the cylinders, okay, left and right, and x2 and x3 is equal to 0, the axis of the cylinder. Now we are asking that what is the probability that the Brownian motion hits this axis, okay, ever, okay, for any time. What is the probability? So we started in the 3-dimension case, correct? So in 2 dimension, at least, if it goes here, it crosses from positive to negative, and then there is a chance that it would cross, but it is in 3 dimension. So this k, I mean this k etc would be just one single line segment in the 3-dimensional space, in the 3-dimensional space. So Brownian motion has 0 probability to hit any line segment in 3-dimensional space. Instead of line segment, if I had a plane, then I could have got the positive probability, but it is just a line segment. In 3-dimensional space, it has 0 probability. Now the map T to Wt remains bounded away from Wn almost surely, therefore, okay, for all n, because it has 0 probability to hit Kn, and Kn is of course a closed set here, and then since Brownian motion path we are looking at, okay, so this is continuous function, and if I take a fixed time horizon, in the time horizon it would be a compact set, okay, because that T would be coming from the bounded domain, so continuous function image would be compact set. So Kn is one side is a compact set, is another compact set, and now we have the T2 property of the Euclidean space, that two compact sets are separated. So there I am going to get that they are separated. However, here when you have that for finite horizon, you can actually extend, I mean, larger and larger every time you will be separated, okay. So we can remain bounded away from Kn almost surely, okay, with probability 1, okay, for each and every n. Kn is a compact set because it is this thing, total line segment is a bounded and closed set in Euclidean space. And Wt, if you look at the graph of Wt, okay, I mean the location, since it is a continuous function and then it is for a finite time interval, that is a compact set, and continuous function takes compact set to compact set, so the image will be compact set. Now Euclidean space has T2 property, T2 topology, because two different compact sets are can be separated. It has T2 separation axiom, correct? Separated with open neighborhoods. So you would be able to say that, okay, Wt would be bounded away from Kn almost surely with probability 1. With probability 1, we are going to say that, okay, it is not going to touch Kn. So what we do is that we do the following thing: we choose epsilon sufficiently small so that the Brownian motion is touching Fn. Fn is that cylinder, okay, this type of looking cylinder, So I cannot assure that it will be 0, probability will be 0. I cannot assure because it could be as close as possible, it could be, but I cannot say that because it has epsilon in, so it has positive width. But for some t, and t is also infinite, okay. So for finite horizon, I can say that, okay, that for some epsilon n, okay, so that probability would be small, but infinite this thing is there. So I can assure that with this given n, 1/3 of n, 1 upon 3 to the n is a very small number, okay, and this epsilon n can be chosen sufficiently small such that this fn shrinks to kn so close that the probability that wt hits fn, the probability becomes lower than 1/3 to the n. So this is the way we are going to do. Now as n is increasing, so fn is closer and closer to 0, and then the chance of hitting that is larger. However, we are going to take the probability 1/3 to the power n is becoming larger and larger, the probability we are going to set even smaller. So the epsilon n should be even smaller, okay, even smaller, and that is always possible. Why? Because kn is the limit of fn. For kn, the probability is 0. So as with epsilon n goes to 0, that probability that hitting fn goes to 0. So from that, I would always be able to find out some epsilon n for which the probability is non-zero, but okay, less than 1/3 to the n. So that is the construction choice of epsilon n. And then if we compute this probability that sigma d is equal to 0, w0 is equal to 0. So this conditional probability. So this conditional probability is smaller than this probability. Why? Because this is a larger event. This set is a subset of this. What is this? This is saying that, okay, ft hits fn for some t. So here and n for some n, okay, for some t and for some n. I mean, this is surely outside the domain of d. If wt ever crosses this, then of course sigma d, I mean, then of course it goes beyond the domain d, okay. And for this to happen, for arbitrarily small time t, the Brownian motion should exit the domain, and when it exits the domain, okay, so that is a subset or sub event than this event that wt touches fn, okay, for some t and for some n, okay. So here we are not putting the constraint that, okay, for arbitrarily smaller t it hits, etc. We are not putting any constraint. So it is a much larger scope, okay, just saying that, okay, wt ever touches fn for some n, okay. So this is but here we are putting lots of constraint, right, because it must leave, and then when it leaves, it touches, then we are trying to find out the infimum, and then infimum should be 0, that means it touches very fast, etc. So we have this thing, this very crude upper bound. However, this crude upper bound is sufficient for us. Why? Because we know its probability. Its probabilities are 1/3 to the n, okay, and this is a geometric series. The geometric series sum is 1/3 to the n. N is running from 1 to infinity, not 0. So 1 to infinity. So 1/3 plus 1/9 plus 1/27, etc. So 1/3 should be taken common, so that we get 1 plus 1/3 plus, etc. And then that series sum is 1/1 minus 1/3, and the whole multiplication is half. Half is less than 1. So what we have obtained is that this is strictly less than 1. Now Blumenthal's 0-1 law is saying that this must be 0, okay. So the 0 is an irregular point, okay. So what is happening here, that since although 0 is in the boundary, but the complement, the d complement is very narrow, attached to 0, very narrow. So it would very fast, the Brownian motion would leave the domain very fast. The probability is also low, it is 0, okay. So that is the point, that if your point A is on the boundary such that your domain is like almost like everywhere, almost like everywhere. So, first example was that boundary was inside the domain, actually, you know, boundary was just a punctured disk, the punctured center. Then everywhere domain was there. So, then that was irregular point. Now, here it is not everywhere. I mean, in one particular direction, of course, the complement of the domain is reachable. However, it is very, very narrow. It's coming very narrow way. Okay. So, here say for example, a complement is this part. Okay. So, there is a, but if you think that, okay, very narrow way, very, very narrow way, okay, arbitrarily narrow way, then apparently it is like everywhere the domain is there everywhere. Okay. Okay. So, there is an irregular point.